Hi everybody, in this video I am going to go through our lesson on growth and decay, and what I want us to start off with is talking about how to find the percent by which two values are increasing or decreasing. So this is what we call the formula for percent of change. And so to find how much you've changed from one value to another, you will simply subtract the new value minus the old value and divide that by the old value. And we're going to look at that in an example here. So let's say the cost of a burger changes from $5.50, oops, to $7.25. So let's find this percent change. So the percent change, in this case, it's an increase because we are going up from originally $5.50. So that's the old price, and the new price is 725. So the percent change is going to be the new value, which is 725, minus the old value. Essentially, what's the difference from the new value to the old value? How much did we change over the old price? So what percent of the old price did we increase in this case? Because the price went up. So let's see, 7.25 minus 5.50 or $7.25 minus $5.50 gives me a difference of $1.75 is how much we increased over the original $5.50 price. And if I actually divide, this tells me that it is increased by about 31.82%. The decimal you would get is 0.3182, blah, blah, blah. So I would move that decimal two places to convert to a percent. And of course, this was an increase, again, because the price went up from $5.50 to $7.25. I want to talk a little bit more about exponential growth versus decay, and we did talk about this in our last lesson, but it is worth mentioning again. Exponential growth versus, oops, exponential decay. So exponential growth, you will see with the equation y equals a times 1 plus r to the t power. And decay is y equals a times 1 minus r to the t power. And from our last lesson, we kind of talked about this. A is the initial value that you start with. R represents the rate at which you are growing or decaying, and we write this as a decimal. And T represents the number of times that we are multiplying or dividing at this rate. So with exponential growth, you'll note that this number raised to a power, this 1 plus r, will result in a factor that is bigger than 1 or a b value that is bigger than 1, whereas 1 minus r will produce a b value that's between 0 and 1. Now we have some real life applications that we're going to work with in terms of growth and decay. So a common application we often will use with growth is compound interest. So our compound interest formula in general is A is equal to P times 1 plus R to the T power. where A represents the money that you have, the account value over time, the amount. P represents the principal value or the initial amount that you put into the account to begin with. R is your annual interest rate. And T is the number of years that you've been accumulating interest. So this is a compound interest. This is what we call the annual formula, or this is compounding annually. And the equation is A, or the amount, is equal to the principal times 1 plus the rate to the t power. Now that is an example of growth. A real world example we see oftentimes of decay is radioactive decay. Otherwise known as a half-life. So our half-life formula is y is equal to A times 1/2 to the t divided by h power. So this is somewhat similar to the interest formula, but also a little bit different. So we still have this A, which is representing the initial value, in this case, the initial amount of the substance that is decaying, usually in grams, like some sort of weight. And then the 1/2, that is, we're dividing in half, right? The amount that we have is dividing in half. And now the exponent, t, is the amount of time that has passed over h, which is the half-life. So if you know the half-life of a substance is 10 days and you want to know how much time or how much substance will be left after 30 days, well, then your exponent would be 30, the time that we are interested in days, over the half-life of 10 days. Every 10 days, it is dividing in half. So this half-life, I really like to think about it as how long until divides in half again. All right, so let's look at some examples. Example number 1. You own a small business that currently has 254 clients. This is expected to grow by 2.3% each year. How many clients will there be after 8 years? Oops. So we have the small business. We currently have 254 clients. So the initial value that we're starting with here is 254 people, and it is expected to grow by 2.3% each year. So this is growth by 2.3%. So if I'm going to write this as a rate, our rate is really this percent as a decimal. So that would be 2.3 divided by 100, which is really like 0.023. Move the decimal 2 places to the right. Sorry, I was getting my left and rights backwards as I was watching myself. So you had, oop, I always like to just divide by 100, but that's me because sometimes the decimal places mess me up. But 2.3 turned into a decimal, it's going to be a smaller number. So it will be moved to the left to become 0.023. All right, so this is our R value, which is going to be then added on to 1 because this is exponential growth. So our formula is y equals a times 1 plus r to the t. A is 254. So this equation that I'm going to write to help me with this is y equals 254 times 1 plus that rate we just found, which was 0.023 raised to the t power. So this equation models the entire relationship. I am interested in specifically how many people we will have as clients after 8 years. So when t is 8, what is y? So please take the original equation that we have written here, 254 times 1 plus 0.23. If I actually add inside the parentheses there, 1 plus 0.23 is literally just 1.023 raised to the t will be 6 power. And I'm going to use Desmos for this, and I really encourage you to do the same. So I'm going to take the original equation, 254, and then we have 1.023. It'd be the same thing if I added 1 plus 0.023. And I'm going to raise that to the 8th power because I'm interested in how many clients we'll have after 8 years. Now I get a decimal. I get 304.6763, blah, 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 blah. Oops. I accidentally wrote 8 here. We were interested in when t was 8, not 6. So the number I got was 304.676 dot dot dot. And this is clients, so I can't have a decimal of a person. So I'm going to just round this up to the nearest whole number and rounding up because actually there's a number greater than 5 after the decimal place. So this is about 305 clients in 8 years. All right, number 2. A study found a population of armadillos decreased from about 3,800 to about 3,610 in 1 year. Predict the population in about 15 years. Oh, in about 15 years. Kind of ran out of space there. All right. So of course, we're assuming that this is constantly decreasing at the same rate. So this is kind of a prediction because it's probably not going to be constantly decreasing at the same amount, but I don't even know what the rate that we're decreasing by is. I just know that we're decreasing. So the exponential decay formula I'm going to use to help me here is y equals a times 1 minus some rate to the t power. And I actually already know t is going to be 15. And our initial population, it decreased from about 3,800. That was the original population, or the A value. And 1 year later, we now have 3,610. So the new population, if you will, is 3,610. So I'm going to find the percent of decrease here. So the percent decrease, I'm going to find what was the difference between these 2 years. So I am actually just going to subtract the new amount, which is 3,610 minus the original, which is 3,800. And then that will be divided by the original to figure out how much did it change from what we originally had. Now the difference between 3,610 and 3,800, make sure I'm looking at the right line so I don't mess this up, is negative 190. And you should get a negative number because it's decreased in that 1 year. So we decreased, we have 190 less armadillos in comparison to the 3,800 we had to begin with. So if I express this as a percent, this is a decrease of about 0.05. So I'm going to turn that into a percent. I can really just take this and multiply it by 100. So our rate is 0.05 times 100. Or I'm going to take the decimal and move it 2 places to turn it into a bigger number, which tells me that we are really decreasing by 5%. Now, that percent was just for my knowledge. I really need the rate, the decimal rate for my formula. So I could have stopped here if I wanted to. So within my formula here, I'm going to write this formula kind of down here. Our population of armadillos is equal to the original amount of 3,800 times 1 minus this rate of 0.05 each year raised to the t power. So now using this rate to write kind of a nicer equation, this is going to be still 3,800 times 1 minus 0.05 is 0.95. 1 minus 5 hundredths is 95 hundredths, and that is raised to this t power. So again, I need to let t equal 5. So I'm going to substitute in 15. We're interested in 15 years. So I'm going to let t equal 15. So in Desmos, I am going to type 38,000 times 0.95, and I'm going to raise that to the 15th power. Let's open up Desmos again. So the original population, 3,800, or 3,800 times 0.95, it's decreasing by 5% each year, raised to the 15th power. We're going to have 1,760.5 armadillos. So if I'm rounding to the nearest whole armadillo, I could round up. So let's see. So this is about 1,760.506 ... So that is about 1,761 armadillos. Number 3. $2,100 is placed in an account with an annual interest rate of 6.3%. How much will be in the account after 24 years? Assuming this money in the account has not been touched at all, and that our interest rate is remaining the same. So let's write a formula for this. This is annual interest, so I can actually use this formula that I have up here. A equals P times 1 plus R to the T, or the amount that we have is equal to the principal that we put into the account times 1 plus that rate, the percent as a decimal, raised to the t power. So our principal, the initial value we have, in the account is $2,100. And the rate is 6.3%. So I'm going to turn that into a decimal by taking 6.3 and dividing it by 100, or moving the decimal 2 places to the left. And that will give us a rate of 0.063 being added on each year. So our formula that I'm going to write using this principal and this rate will be A equals 2,100 times 1 plus 0.063 raised to the t power. Now, of course, I can add 1 plus 0.063, and that will get me 1.063 raised to the t power being multiplied by 2,100. Now we are interested in the money we have after 24 years. So when t is 24, what's the account value? How much money do we have in the account? So I'm going to take 2,100 and I'm going to multiply it times 1.063 raised to the 24th power, because I want t to be 24. And when you put that into your calculator, or you put that into Desmos, you will get that the account will have $9,000. Sorry, $9,099.50. And using Desmos is a wonderful tool for this. And when I use Desmos, oops, I didn't mean to do that, but that's okay. I can simply type 2100 or 2,100 times this 1.063 and raise that to the 24th. And it's $9,099.502. So that's going to round to 50 cents because I can't have anything past that hundredths place. All right, we're going to do one more problem together. Problem number 4. A substance has a half-life of 8 days. How many grams of a 500-gram sample will remain after 35 days? Round to the nearest hundredth. Oh, 10th, sorry. Round to the nearest 10th. So we are going to use the half-life formula, and the half-life formula is this y equals your initial amount A times 1/2 to the t over h power. I'm going to write that down. It is y equals the initial amount times 1/2 to the t over the half-life, the time over the half-life that it takes for it to divide in half. So the initial amount, or A here, is the 500 grams that we have to begin with. Our half-life, or H, is 8 days, because that's how long it takes for it to divide in half again. And we want to know how much will be left when T is 35 days. So H, that is my half-life, which the problem says it is a half-life of 8 days. And we are interested how much will remain after 35 days, or when T is 35. So the formula I'm going to use, I'm going to simply substitute everything in. Y is equal to 500 times 1/2 times, or to the, sorry, T is 35 over 8 power. So when I put this into my calculator, because you can simply put this straight into your calculator, this will tell me how many grams are left. If it's dividing in half every 8 days, and we are waiting 35 days, essentially, how many times are we going to multiply it by 1/2? That's what the 35 divided by 8 is doing. The 35 over 8 is basically telling you how many times is this half-life going to happen if it's every 8 days. So let's put it into Desmos for the final time. So 500 times 1/2, I'm going to do 1 divided by or over 2. And then outside of the fraction in my exponent, I'm going to have 35 divided by 8. And notice how 35 divided by 8 is in my exponent. I could simply find what 35 divided by 8 is, 4.375, and I could raise this 1/2 to the 4.375 power, and it would be the same thing. So let's see, 1 over 2 raised to the 4.375 power. And we get 24.097 grams. And we were asked to round to the nearest tenth. So the amount we have left, or y here, is 24.097 blah, blah, blah grams, which is approximately 24.1 grams if we're rounding to the nearest tenth of a gram. Please let me know what questions you have. I am really looking forward to continuing to work with this in class with you. And again, email me if you need anything.